Bam! Mr. Taru. In this video, we're going to be doing 5 examples involving simplifying square roots that involve variables. In the description, you'll find timestamps to jump ahead to each of these 5 examples if I happen to start off with something that's maybe not really what you're interested in, and you'll also find links to old videos that I've done related to this content. Actually, maybe some of them are not that old, but let's get started. We're going to first remember a few of our properties of square roots that actually apply to all radicals. But we have the square root of a times the square root of b is equal to the square root of a times b, and this property also works in the reverse order. We're going to be assuming that a is greater than or equal to 0, and also that b is equal to or greater than or equal to 0. That's because this example is, or this video is only involving examples that deal with answers which are real numbers. Now we also have that the square root of a divided by the square root of b is equal to the square root of a divided by b. Now, for our expression here, we need to assume that the numerator is a value which is greater than or equal to 0, and that our denominator is defined to be a value which is just greater than 0. We can't include an equal sign because you can't divide by 0. And like we just discussed in our other video, simplifying square roots that involve numerical values, that the square root of a squared. Okay, so we have an even power applied to a variable or a value that is, well, inside of a radical which has an even index. In this case, that it's an index of 2. Well, that square root of a squared acts as an absolute value function. Now, this is not a proof, it's just an example, but we have something here like -3 squared, and because the negative is inside the base, or inside the parentheses, which is defining the base of our power of 2, that's going to be equal to -3 times -3, which is, of course, equal to +9. Now, if we go in that reverse order, or take the inverse math operation, and take the square root of 9, well, we don't get exactly an inverse situation here because we have an answer that's 3, almost the same as what we started with, but, well, the negative went away. So thus we have the fact that -3 being squared inside of a square root function, actually that's equivalent to the absolute value of -3, which is equal to +3. So we'll have to be aware of this as we do our problems here of simplifying these square roots that involve variables. Now, your textbook may make this look simpler than I'm actually discussing, because sometimes in early algebra books, in the directions, they just make the assumption that our variables are all going to be greater than or equal to 0, thus kind of making this unimportant, or not unimportant, but redundant. Now, it is incorrect. While we can multiply square roots and get a product, is very straightforward, the same with division, that's not the same with addition and subtraction. So it'd be incorrect to say that the square root of a plus or minus b, even though this is only plus here in my writing, is not equal to the square root of a plus the square root of b. There is no sort of property of addition and subtraction with our square roots, or any radical for that matter. All right, let's get on to our examples. Example number 1, we have the square root of 2x times the square root of 6. And we go from sort of, simpler to more complicated examples through the video. Okay, well, we can use this multiplication property for square roots and just multiply these together. We have that the square root of 2 times the, actually let's write this out, the square root of 2 times the square root of 6, and then that is going to be multiplied by the square root of x times the square root of x. Now that comes out to be 2 times 6, which is 12, times, and I'm just going to extend that square root symbol, x times x, which is x squared. Now, this is not our final form of this answer because, well, we have some perfect squares that's inside our square root. Thus, this expression can be simplified. We have a factor of 12, which is a perfect square. 2 squared is equal to 4. And of course, we can see that we just have x squared, so that itself is a perfect square. So this can be, again, using our property of multiplication for square roots, written as the square root of 4 times the square root of 3, of course, because 4 times 3 is equal to 12, times the square root of x squared. Well, the square root of 4 is 2. The square root of x squared, we just said that that acts as an absolute value function, is equal to the absolute value of x times the square root of 3. But this is not actually how you're going to see or need to write your final answer. You see, when we look at our original problem up here, when we see this expression of 2, and actually it's not really important, when we look at the fact that we have an x to an odd power, in this case just x, in each of these original square roots that are given to us in our problem, the fact that we're saying, and we can see it here more clearly, that we're taking the square root of x in each of these factors of our one single term, I can't write this unless I'm making the assumption or I'm implying that x in this expression has to be greater than or equal to 0. Otherwise, this isn't even an expression that yields a real solution. So by the way that our original problem is written, we need to be able to understand that we can assume, even if it's not in the directions, that for these to give real solutions, x has to be greater than or equal to 0, which makes the inclusion of the square root, the absolute value notation, in our final answer not really necessary. It's not actually wrong. It's never wrong to use absolute values kind of more often than necessary, but they are redundant. So we can just take these out in our final answer and say that, that the square root of 2x times the square root of 6x is indeed equal to 2x times the square root of 3. Okay, now if we move on to our second example here, the reason why I'm following up with this example that looks not too different than our original one is because we have even powers of 4 and 2 applied to our variable of x. Well, when you take a value and you raise it to a even power, like -2 times -2 is +4. -5 times -5, that's -5 squared, at least if -5 is wrapped in parentheses, is a +25. So here, x can be defined as far as its domain here in this expression as any value, whether it's positive, 0, or even equal to a negative number. So there's no indication here that we know that x is greater than or equal to 0. So how is that different? Well, as we go ahead and multiply this together, we get the square root of 5 times the square root of 3 times the square root of x to the 4th. And we could simplify this now, but I'm going to go ahead and look at it as we go through the problem. And the square root of x squared. Well, the square root of 5 times the square root of 3 is the square root of 15. And I can just, you can leave this in pieces until we get to our final answer or put it all together. We have x to the 4th times x squared, again using that product property for square roots, and remembering that when you multiply like bases, you add the exponents. So x to the 4th times x squared is x to the 4 plus 2, or x to the 6th power. Now, like we had up here, this may be the way that our final answer, is given, that we'll give to our teacher, but it's not the final version of our answer if this expression inside the square root has any perfect squares in it. Are there any perfect squares which are factors of 15? 1 and 15, 3 and 5. No, none of those numbers are perfect squares. But there are x squares in this x to the 6th. And there's a lot of flexibility in how you show your work with working with radicals. Since we're just starting out, I'm going to sort of expand it out into a bunch of little tiny pieces, hopefully making it make as much sense as possible. Almost actually kind of going back up to this line where I'm going to separate, since we talked about how the power of 2 and the square root cancel out, in this case if they're both even, acting as absolute value function, I'm going to say that I'm going to write x to the 6th, expand it out where I use bases that have a power of 2 up until either I get just an x or we just basically get to a power of 6. So x to the 6th can be written as x squared, and then times the square root of x squared times the square root of x squared. There's other ways to write this out that doesn't make it look like I'm kind of going backwards. But at any rate, we have the square root of 15 in each of these square roots of x squares acts as an absolute value function. So we have the absolute value of x times the absolute value of x times the absolute value of x. And we can go ahead and use our properties of exponents with this absolute value of x times the absolute value of x times the absolute value of x and write that as the absolute value of x cubed times the square root of 15. Now here, remember, these x's started off with even powers, so there's no implied limitation here that x has to be greater than or equal to 0. Now here with our x cubed, because when you take a negative number and cube it, like -2 cubed, that's -2 times -2 times -2, which is equal to -8, this x cubed could be resulting in a negative number. And we need to take care of that possibility by keeping the absolute value wrapped around that x cubed, where here the absolute value of x was not needed because we had that implied domain, which is x has to be greater than or equal to 0. Now our next example is going to discuss, what happens if you do all this simplification and you have an x to an even power. So let's coming up right now, what do you have to do with those absolute value functions? Example number 3. So here we have a negative in front of our square root. So even though when we're given that radical sign in our textbooks, we're thinking of, okay, we're being asked for the principal square root or the positive root, we do basically have a -1 sitting out as a factor in front of our radical. We can just put that coefficient basically right there. So we have -1 times the square root of 200 times x to the 4th. Okay, now your textbook may again say that for all these problems in our section, let's assume that x's or the variables are greater than or equal to 0. We're working under the assumption that our directions do not say that. We have x to the 4th, and the sign of a number, like whether it's positive or negative, any number that is raised to an even power by default becomes positive. So here, x, the domain of this expression basically is that x can be any number, positive, negative, or 0. Now, keep that in mind as we go through our problem. We're going to simplify this expression by identifying if there are any values, any factors within 200 or x to the 4th which are perfect squares. Well, of course, there is a perfect square in 200. 110 squared is equal to 100. So we're going to write the square root of 200 as the square root of 100 times the square root of 2. And then we have x to the 4th being written as the square root of x squared times the square root of, again, x squared. So we're, again, using that multiplication property of square roots where we're actually basically undoing the multiplication, factoring. Now, the square root of 100 is equal to, of course, 10. So we have -10 times the square root of 2. We have this power of 2 and the square root, or the second root of x squared. When that index and that power are both equal to 2, remember this acts as an absolute value function, so the square root of x squared is equal to the absolute value of x. And again, we have another times the absolute value of x. Well, we can go ahead and multiply these together and say that the absolute value of x times the absolute value of x is the absolute value of x squared. So now we're looking at -10 times the absolute value of x squared times the square root of 2. Now, do we need to keep the absolute value symbols around the x squared to imply that, well, this factor has to remain positive? Well, no. Again, any number that is squared is going to come out as a positive value. So again, here the absolute value symbols are, or function is redundant, so we can just write our final answer as -10 x squared times the square root of 2. And that is our answer for example number 3. Now over here, with example number 4, we have the square root of 24 times x to the 4th over the square root of 3 times x. And we have the same variable in the numerator and denominator, x. And 3 is a positive value. or factor of this term of 3x that's inside the square root that's in the denominator. There's no plus or minus here. Technically, this whole thing is a single term, but look in the denominator. Well, for me to write this, and understanding that we're only working with radicals or square roots that are going to give us real solutions or real values as an answer, this x times positive 3 that's inside the square root is implying from here that x is greater than or equal to, actually not equal to 0 because you can't divide by 0, but x is greater than 0. So we're not going to need to leave any absolute value function symbols in our work as we work through this and write our final answer. So we're going to write this as the square root of 24 times x to the fourth over 3x. That is going to become, well, 24 divided by 3 is equal to 8, so we have the square root of 8. And when you divide like bases, you subtract those exponents. And if you're uncomfortable with that, we have x to the fourth, which is x times x times x times x. There's 4 of those bases being multiplied together, divided by x, and anything divided by itself is equal to 1. So x to the fourth divided by x to the first is equal to x to the 4 minus 1, or x to the third power. One more time, if this expression of 8x cubed has no factors which are perfect squares, then this is the simplest form, an exact form of our answer. But no, there is a perfect square in 8, that is 4. So we have the square root of 4 times the square root of 2. Remember, 2 times 4, of course, we know is equal to 8. And let's expand out this x to the third to be some kind of x squared times x squared times x squared, so on and so on, until maybe you need a x at the end where you get a power of 3. Well, x to the third is equal to x squared, and of course we're dealing with inside a square root, so the square root of x cubed is equal to x, the square root of x squared, times the square root of x. The square root of 4 is equal to 2, so we have 2 times the square root of 2. We have the square root of x squared, the square root and the square acting as absolute value symbols, which I'm going to temporarily put in here. So this has given us the absolute value of x, and then we have times the square root of x. But we don't need to leave the absolute values wrapped around this variable of x, because in the original problem, with that x to the odd power inside the even root, that square root, that implies that x needs to be greater than or equal to 0, or in this case, because it's in the denominator, greater than 0. So this is not needed. Our final answer is going to be 2x times the square root. Now let's bring this together. The square root of 2 times the square root of x is the square root of 2x, and that is our final answer. Okay, now let's move on to the last example right now. It's the last example that we have. The square root of 48 times x to the fourth plus the square root of 12x to the fourth. Now, we talked about how there's no addition property for square roots or radicals in general. The square root of a plus b is not equal to the square root of a plus the square root of b. But you can add terms which have square roots in them. You just simply have to simplify, if possible, those square roots or those radicals so that they have the same expression inside the radical or square root. And if we're talking about general radicals, the index has to be the same. These are both square roots. They both have an index of 2. Okay, so the square root of 48 times x to the fourth. Let's go ahead and get that simplified. And we have these variables of x's being raised to even powers, which always are going to yield a positive answer no matter what the value of x is. So arguably the domain of each of these square root expressions is, that x can be any real number. And actually this whole expression is combined of these two square roots, so that is the domain of this entire expression. Are there any perfect squares in either of these numbers? Well, yes. For 48, we have 4. Well, we also have 16. So we have here, I'm doing some mental math as I'm thinking. We have, 48 divided by, let's go ahead and, why did I pause there for a second? 48 is equal to 4 times 12. Well, I paused right there because 12 has another factor of 4 in it. 12 is equal to 4 times 3. So we have 4 times 4 times 3. Now, I'm not talking about like some kind of prime factorization tree, which actually is not necessarily a bad idea, but I'm just running through my head what are some perfect squares which are factors of 48. And when I said 4 and thought out loud 12, well, I paused because 12 also has a perfect square in it as a factor, again, which is equal to 4, and 4 times 4 is 16. And, well, you can say that 48 is 2 times what? 24, and that 24 is 2 times 12, and then you've got 2 times 2, and 12 is 2 times 6, and then you've got that 6 is 2 times 3, and here we have 2 times 2 is 4, times 2 is 8, times 2 is 16. Just a little random tangent there. But we have, anyway, the square root of 16 times the square root of 2 times... And yes, I just realized that I wrote 2 here when I meant to write 3. Let's go ahead and get that fixed. Glad I didn't continue on with that error. Okay, so we have the square root of 16 is equal to 4. We have the square root of 3. The square root of x squared, as we discussed, gives us the absolute value of x. We have another times absolute value of x, plus the square root of 4 is 2. We have a square root of 3. And one more time, each of these two factors of the square root of x squared, yielding us 2 factors of the absolute value of x. And just like in the previous example, the absolute value of x times the absolute value of x is equal to the absolute value of x squared. Now, do we need to keep the absolute values wrapped around our simplified expression here, or factor of x squared? No, any number raised to an even power comes out to be a positive value, thus the square roots, keep saying that, thus the absolute value function notation there is redundant, so we're looking at 4, try that again, 4x squared times the square root of 3 plus 2x squared times the square root of 3. And we're looking at 2 terms separated by this addition sign. Each of these terms both have a common variable, or a like variable of x. Each of those x's have the same power of 2. And we have both of these terms having a factor of the square root of 3 with the same index of 2 and the same value, which it could have a variable too, but with the same expression inside both of the square roots of 3. So these are like terms, and adding like terms, we can factor out, I'm not sure, you might just do this automatically depending on where you are in your journey of algebra, but each of these 2 terms have a common factor of x squared times the square root of 3. So we can factor out those common factors and say that we have taken out that common factor of x squared times the square root of 3. Taking that out of our first term, we have just left with 4x squared times the square root of 3 divided by x squared times the square root of 3. Just, of course, leaves us with a 4. And over here, with our second term, that's going to leave us with a 2. And of course, 4 plus 2 is equal to 6x squared times the square root of 3. I'm Mr. True. Bam! Go do your homework.